All right, so today is the 27th of September. Yep. And so what we're looking at here is the Bitcoin chart, and I have my operative script overlaying it, and I was looking at the performance just this past week. It made a couple of really beautiful entries, exits. It entered right here, rode this wave, exited here, avoided this whole drop, and then it did this. It entered at this point and got dragged down, what is that, 5.5%, right? And the reason this especially got under my skin is because of where and when it actually happened. So what my strategy is actually evaluating at all times, it's looking at the slopes of the blue and red lines right here, which are both 28 period EMAs on their respective time frames. The blue one is on the local 4-hour, which is what it's running on. The red is referring to the 2-day 27 period EMA. And the way it's supposed to work, it's meant to work, the spirit of it is that if this ever has a negative slope, it will not enter long. It always requires this to have the red line or the blue line to have a positive slope in order to enter. Now, if you actually looked in on this in real time, at this exact moment when it entered the trade, this would have had a negative slope. So why did it do this? Well, it's doing exactly what I coded it to do, in fact, because when I'm referring to a higher time frame, I have to use something called a security call. And the way these work, in order to avoid what's called reprinting, I might be using a lot of jargon you haven't heard before, but reprinting is basically when you are drawing information from the future that doesn't exist at that time at the historical bar. So if your script is repainting, or if it's improperly using the security function, it's going to give you unrealistic backtest results that you can't trust. It's going to give you, fluffy numbers, right? So you want to avoid doing it, but I also want to avoid situations like this. So it gets me thinking, is there a way that I can apply the exponential moving average to avoid lag and also not reprint, right? I want to refer to this 2-day 27 period moving average and get a real-time assessment of whether this is a positive or negative slope instead of just having to wait till the close of the next 2-day. That's why you have this step function here, right? So what I did first, let's take this off, put this up. So one thing I really like about PineScript is that you can go to their reference book. You can go here and you can search EMA, and they'll tell you exactly, quantifiably, how they calculate their built-in EMA function. When you use that built-in EMA in your script, this is exactly what it's doing. And so I can actually go and I can copy and paste this right into here, and then I can compare it to the built-in EMA function. So I made this script that will print 3 EMAs that should be the same. It's got the built-in EMA script that's colored in aqua or cyan. It's got the specified pine EMA script that I copied from right here. That's going to be fuchsia. And it's got my custom EMA script, which has been altered in a particular way that I'll get to later. And that's going to be in yellow. So if I make that visible, boom. So, the red one, we don't need to worry about that yet. That doesn't exist yet. Okay, so just to prove to you that all 3 of those are the same, I can take them off one at a time, see how they're same calculation, right? And what this red one is one using a security call, right? So this is referring to the 2-day time frame like I wanted to do before. But what we're going to do is I'm going to end up using this custom function that's in yellow, and I'm going to input what's called an alpha right here to mimic this step function in such a way that it is actually more efficient and better to use in the script. Okay, so how do we do that? And what is this alpha function? All right, so we go back in here and we look at PineScript's code, how they calculate an EMA. It uses something called an alpha, right? So it's kind of important to understand the distinction between an infinite impulse response and a finite impulse response. And I'm not claiming to be an expert on digital signals processing or any of that stuff. I basically just teach myself what I need to know to do things I want to do. I know just enough. I don't know a lot. All right. So an infinite impulse response, which is what an EMA is, it never fully abandons the historical information, all that past data, whereas a finite impulse response, like the simple moving average, for instance, if I set it to a length of 10, all of the data, all of the inputs to that function are in that 10 period window. You set it to a length of 10, all the data is in that 10 period window. But with an EMA or an infinite impulse response, it's infinite. It has a trail basically of data that it deprecates over time. So all that data from like 1,000 bars ago, it's never fully deprecated from the current output, but it just gets asymptotically less relevant, right? So that's kind of the distinction, right? And the way it's calculated, actually, look at this is the simpler calculation. So the source here, that's the real-time most present data bar times the alpha plus the previous value of this EMA times the remainder, the inverse of the alpha, right? 1 minus the alpha. So the alpha is always some float between 0 and 1, right? So what percentage of that new data are we going to weight into our function at the expense of the old data? Okay? And that alpha is what determines that weight of that new data. So what we're going, and it's bound by this equation here. What really defines an EMA versus something else like an RMA, for example, which is also an infinite impulse response, is this equation here, 2 divided by n plus 1, quantity. Quantity of n plus 1, take 2, divide it by that. So what I can do is I can flip over to Excel, and I can do one of these doohickeys, all right? So up here first, pretend we wanted to execute on the 1 hour. And I wanted what I have highlighted here. This is my 2-day, 27 period moving average, like that red step line that I had shown. We can calculate what that alpha would have to be using that equation, 2 divided by n plus 1, where n is simply the number of periods I want times the number of 1 hours in a 2-day, which is 48. So 48 times 27, that's our n, which is 1296. N plus 1, take 2, divided by, you get the alpha, right? So we can actually use that to make kind of complex ratios, right? Let's say you want to do, you like Fibonacci, people do, and you wanna make a daily like Fibonacci, a bunch of Fibonacci bands on the EMA. But you want it to operate not on the daily. Let's say you want to operate it on the 4 hour. How many 4 hours are in a day? 6. I can set this 6, and I wrote this up so it'll tell me what alpha to use here. So if I wanted a 1-day moving average from the 4 hour, I would use an alpha of 0.2857, etc., all the way down. So over here, or you can use, what's really cool about using the alpha instead of the typical lengths is it's because it's a float, you can use like these intermediate time frames. Like you can say, hey, the 2.71 day length EMA, which isn't possible with the default inputs, right? If you have to use an integer length, this isn't quite possible. So I just wanted to highlight why that was kind of cool. So what I did here, so this 54, 55 kind of equivocates to what I was calculating already. So I'm going to end up using this alpha that I've calculated, 0.00609, basically, and I'm going to put that in to the formula to get a real-time apprehension of what that other time frame is doing. So if we flip back, I demonstrated that these calculations are the same. So let me show you this other script I made. This is using those ratios here. So we have E, this is E squared, E cubed, etc. Okay, this is the translated to the local. I'm on the 4-hour, so there are 6 4 hours in a day. So if I wanted the 2.718 day EMA calculated on the 4-hour, put the number 6 in here, here's our alpha. So I can take that and I can put it in here anywhere I want, and it will show me that. Here, let's reset these so you can see. So here are those Euler ratios, right? So even though I'm on the 4-hour, I can print a 2.718 length daily EMA. That's the white line. And you get this one, that one, and all these other ones. And this green one here, that were 57.598 length EMA, which just about equivocates to the line I wanted. This red stuff here. That's why I took all this off. Right? Isn't that lovely? So you can see now I programmed it to change color when the slope changes. So if I had been using this method, instead of depending on the security call, if I had used this method with the custom EMA function using the alphas, I could make it so that it would not have entered right here. It would recognize, hey, even though this 2-day candle is not complete, its slope is effectively negative at this point in time without repainting. And it would not have entered here, and it would have avoided this 5.5% loss. So what did I do? So I took that and I implemented it in a new version of the script. And when I backtested it, it actually performed less. So I'll have to do a more in-depth investigation as to why that is. It still performs well. It's still good enough to use, but I don't know whether. So if you look at these strategies, the other one was like 40% and what I don't know though is that could just be like one random trade, but because it's from 3 years ago, early on in the script, the effects get magnified. So just because it performs less doesn't necessarily mean it's worse. I gotta isolate time frames and really figure out what's happening there. But at the very least, I achieved what I wanted. Here, I'll show it to you. Let's what did I call it? Liquid. Here's that. Give it the same settings so you can honestly compare it. There we go. And voila. It's doing the same calculations as the original strategy was. It's doing the same calculations as the original strategy, but it's using this continuous EMA rather than that step function. And you can see it avoided the ill-fated entry right there, which is what I wanted it to do. So that's kind of an example of some of the cool stuff you can do if you are willing to go in and kind of deconstruct those custom functions. You could reconstruct them with slightly different math and kind of game how other people are trading, because you know everybody else, they're just using this other method, and if you can be nimble and kind of work around them, you can outperform them on the market, right? Oh, so one aspect I failed to really show you, which is pretty cool about doing this when you do it this way. So these are all referring to the daily. I didn't show you the code. Okay. So what I did here, I actually, because we know the 2 over n plus 1, and we know how many minutes are in a day, right? 1440. Then no matter what time frame I move it to, as long as it's less than a day, I can calculate with this formula exactly what the alpha would have to be to equal these ratios, which are what these equations are right here, right? So the effect that has Notice, let's go to the 12-hour and notice where the moving averages are, right? Notice their behaviors, and now I'm gonna drop down to the 4-hour. See how they stay the same? Go to the 1-hour. And they're still there. Isn't that cool? You can't do that. Can't do that normally. So I thought that was really cool. And if maybe you're not a fan of these weird ratios, you could make these anything you want. Like say, okay, I'm interested in the 1 day, or I'm interested in the 7 day, maybe the 28 day, you know, what, like 180, 360 perhaps. Right? That works pretty well, right? And they're all referring to the daily time frame. It does all the math for you, so you can get these live slope assessments even on other time frames, which I thought was pretty cool. So that's all I had to show for you, I suppose. I hope you guys think that's as cool as I do. I really like it, and it gives you kind of a glimpse of what else I'm doing, even the stuff I'm not showing you, because a lot of it is just, okay, take these classical functions and break down the code, deconstruct exactly how that function is calculated, and then reconstruct it with a slightly different method, right? Because a lot of these functions that are really popular were made in like the 60s, and the math has been improved somewhat, but people haven't adopted the newer math. So there is game theory at play in the algo trading world. All right, so that's what I wanted to show you. I guess that's it for this video. I'm gonna rewatch this and see if I'm happy with the way it went. But all right, until next time.